Welcome to Lecture 24. In this lecture, we're going to be talking about scattering resonances or Feshbach resonances. We're going to be doing this by looking carefully at the example of the exact solution that we got from the delta shell potential that we worked on in the last lecture, in Lecture 23. So just to remind you, the last time we showed for that delta shell solution that at low energy we had this relationship for the scattering phase shifts that tan delta L of K was proportional to Ka raised to the power 2L plus 1. This power law at low energy is called the Wigner Threshold Law, and it shows that the S-wave scattering is the dominant scattering at low energy. Now, generically speaking, we parameterize the low energy scattering with something that's called a scattering length and something that's called an effective range. And I've summarized for you what they are right here. The defining condition is K to the 2L plus 1 multiplied by the cotangent of delta L of K is going to equal minus 1 over A sub L plus 1/2 K R sub L squared plus higher order terms in K. And the numbers A sub L and R sub L are constants. When we let L equals 0, the specific one, A sub 0, is called the scattering length, and the specific one, R sub 0, is called the effective range. So this is just a set of definitions here. If we want to actually figure out what this is, we're going to have to plug in what those partial wave scattering phase shifts are and plug it into this formula above in order to determine what the scattering length and the effective range is. So we're going to actually go ahead and do that now. If you recall, what we found was that tan delta L of K was equal to lambda A times Ka to the 2L plus 1 divided by 2L plus 1 double factorial squared times 1 over 1 minus lambda A over 2L plus 1 for that delta shell potential in the limit where Ka was very small. Now we can take that, we take 1 over that to plug into the formula above, and what we find is K to the 2L plus 1 cotangent delta L of K will equal the quantity 2L plus 1 double factorial squared times 1 minus lambda A over 2L plus 1 divided by lambda A times A to the 2L plus 1. We can extract from this what AL is. We don't have the higher order terms in Ka, which we would need to get the effective range. So we're not going to be looking at the effective range in this lecture, but we can immediately get the scattering length because it's minus 1 over the term on the right-hand side. So A sub L is equal to lambda A over 1 minus lambda A over 2L plus 1 times A to the 2L plus 1 divided by 2L plus 1 double factorial squared. We're going to now look at L equals 0 because that's the situation where we have defined what is called the scattering length. And what we find is A0 is equal to minus lambda A over 1 minus lambda A times A, or it's equal to minus lambda A squared over 1 minus lambda A. Now, you note that as we go through lambda A equals 1, this scattering length is going to have a divergence. And furthermore, the higher partial waves are going to diverge when lambda A is equal to 2L plus 1. This means that the scattering length can become much larger than the range of the potential when we're close to these critical values of the scattering. And these resonances are called Feshbach resonances after a famous MIT professor who was the first person to work on these. In atomic physics, you can tune an external magnetic field to go through these Feshbach resonances. And this becomes very important in ultra-cold atomic physics because it can be used to govern what the interactions are between the atoms, or essentially allow us to tune the interactions between the atoms and allow us to look at experiments where you change the interaction between particles essentially on the fly, which is really a pretty cool idea to think about it. In the solid state, electrons have a fixed charge. We can't really just immediately change the charge on an electron and see how interactions would change in a material. But using this Feshbach resonance, we can do it with ultra-cold atoms and study properties of quantum particles when the interaction changes rapidly. Now, if we look at the limit as k goes to 0, sigma of k is going to go like 4 pi sine squared delta 0 of k over k squared, we can substitute in what delta 0 of k is. It's given by lambda a times ka divided by 1 minus lambda a. That will be equal to minus a0 times k. And if we plug that in and look at the limit, we're looking at the limit where the a0 is small here, then sigma of k goes to 0 will be proportional to 4 pi a0 squared, because we did an expansion of the sign a0k and said it was equal to a0k. So the scattering length when we're not on resonance will determine the total cross-section for the low energy scattering. Of course, when we're on resonance, it'll get much more complicated than that. So what is the origin of this scattering resonance? It's really a quite odd thing that is happening in this system. It turns out it's related to the appearance of bound states in the potential. Now, if you go back and recall a particle in a finite square well, you can just think about this in one dimension. You should have solved this problem in the fall semester or earlier in another quantum mechanics class. If you remember from the solution of that problem, as you vary the depth of the potential, you can get more and more bound states inside the potential. And there were critical potential strengths where a bound state would enter right from the energy E equals 0, right from the top of the energy diagram, right where the energy is equal to 0. And then it would move down and move into the bound state, and then eventually another one would pop in and so forth. So there's this phenomenon as you change the strength of a potential where you can create a bound state from a scattering state. And that is the origin of these scattering resonances. So we're going to go into this in detail and look at the detailed structure of how that works for the delta shell potential. So if you go ahead and just plug into the Schrodinger equation for the delta shell potential, this FNL of R, that's the wave function, we have the term when we go into, the FNL is R times the wave function. When we go into looking at this in the Schrodinger equation for the radial wave functions, we find we get minus h bar squared over 2m d squared by dr squared FNL of R plus h bar squared L times L plus 1 over 2mr squared FNL of R. That second term is the centrifugal barrier term, minus h bar squared lambda over 2n delta of R minus A, FNL of R, that's the potential term. It equals ENL of FNL of R. Now, in the situation where we're not at R equals A, this is a non-interacting potential, and the solutions of that non-interacting potential are these spherical Bessel functions, JL of KR and eta L of KR. So when R does not equal A, the energy is going to be given by minus h bar squared k squared over 2m, and we have to analytically continue to an imaginary argument. So it's JL of IKR and eta L of IKR as the solutions of this bound state problem now. These are the solutions for the bound states as opposed to the scattering state solutions, which have the real KR arguments. So the reason why we have to go to imaginary K is, remember, the energy is h bar squared k squared over 2m minus h bar squared k squared over 2m. And the energy when I'm in a free particle that is a scattering state, the energy is plus h bar squared k squared over 2m. It's greater than 0. So in that case, the arguments of the JL of these spherical Bessel functions was given by KR. Here, because the energy is actually minus h bar squared k squared over 2m, I have to let k go to ik in the argument of those Bessel functions, which is why we have that JL of IKR and the eta L of IKR. Okay, we can think of that as just analytically continuing our solutions to imaginary arguments. Now, what we have to do is we have to match the wave functions at R equals A and we have to take into account the derivative discontinuity from the delta function at R equals A. When R is less than A, only the JL function is allowed, because when R is less than A, the eta L function diverges at R equals 0, and we have to have a finite bounded function as R goes to 0. So FNL of R will equal some constant A times JL of IKR when R is less than A. But when R is bigger than A, I can have either linear combination, B times JL of IKR plus C times eta L of IKR. And now we're going to use a trick to figure out what the ratio of B to C is. As I had mentioned, the behavior is fine as r goes to 0 because JL goes like kr to the lth power, and this solution has to go like r to the lth power as r goes to 0. But for large r, we're going to use the asymptotics of those spherical Bessel functions. JL of IKR is going to go like 1 over IKR sine IKR minus L pi over 2. And eta L of IKR is going to go like minus 1 over IKR cosine of IKR minus L pi over 2. You notice those sines and cosines have imaginary arguments. That means they're actually hyperbolic sines and hyperbolic cosines. And we need to pick the linear combination in the large R limit that will go like e to the minus kr, because that's the only case that we will get that will be a normalizable solution. So we have to go ahead and remember that cosine x is equal to e to the ikx plus e to the minus ikx over 2. Sine kx is e to the ikx minus e to the minus ikx over 2I. And then you see that we have to pick c equals I times b in order to get 1 over I times cosine x plus sine x is proportional to e to the plus ix. And then when I let x equal ikr, I will get e to the minus kr, which is the exponential decay. So from this argument of looking at the asymptotic behavior for large r, we have fixed the ratio of two of those constants. So we have fnl of r is a JL of IKR for r less than a, b times JL of IKR plus I eta L of IKR for r greater than a. Now, if you remember back to our solution of the delta function potential, we plugged in these forms for the wave function under the assumption that we'd already gone through this analysis and that this is the right thing to do. So this form should be familiar to you from what we already did with that delta function potential when we were looking at the scattering amplitude. Now, continuity at r equals a just tells us a JL of IKA is equal to b JL of IKA plus I eta L of IKA. And then when we calculate the derivative, we're going to get b times IK times JL prime of IKA plus I eta L prime of IKA minus AIK times JL prime of IKA will equal minus lambda AJL of IKA. So on the left-hand side, we're evaluating the derivative slightly larger than r equals a minus the derivative at r slightly less than r equals a, and we're setting it equal to the integral of the derivative that we get from the delta function, which is minus lambda times the wave function. So it's minus lambda times a JL of IKA. I could have also put in b JL of IKA plus I eta L of IKA, but this is, of course, an easier way of doing that. That's coming from the fact that the wave function itself is continuous at r equals a. Okay, we can go ahead and solve this. What we find is a is equal to b times 1 plus I eta L of IKA divided by JL of IKA. And that's from the first equation. And then from the second equation, we can get that b times JL prime plus I eta L prime minus b times 1 plus I eta L over JL times JL prime is equal to I lambda over k b times 1 plus I eta L over JL times JL of IKA. And we can rearrange this into the form I JL of IKA eta L prime of IKA minus I eta L of IKA JL prime of IKA is equal to I lambda over k JL of IKA JL of IKA plus I eta L of IKA. We're essentially just doing this by multiplying both sides by a JL of IKA. That's going to immediately get you that right-hand side that you see there. When we look at the left-hand side, we'll have a b that has a JL prime plus I eta L prime JL minus b JL prime minus b eta L JL prime. And so you can see we're going to get a cancellation of that JL prime from both of those two terms, and we're just left with the terms that are on the left-hand side. Now, this is the equation that we have to solve to determine what k is for the bound state. And then from that equation for k, we then will determine what the energy is, which is minus h bar squared k squared over 2m. So from that, we will get the energy. So this is a transcendental equation that we have to solve to determine the K values for the bound states. I want you to remember this because we're going to be coming back to this and talking about it a little bit further at the end of the lecture. All right, let's examine this behavior as K goes to 0. So JL of IKA goes like IKA to the L over 2L plus 1 double factorial. That means JL prime, I will just have a factor of L and I have to remove a power of IKA. So that goes like L over IKA, JL of IKA. Eta L of IKA goes like minus 2L minus 1 double factorial over IKA to the L plus 1. So when I take its derivative, I'll get a minus L plus 1 over an IKA times that eta L of IKA. That means when I look at the product of JL of IKA times eta L of IKA, we just look at that first asymptotic form, you find it's going to go like minus 1 over IKA times 1 over 2L plus 1. We're now going to take these results and substitute it back into this expression here. Maybe I can get it all on the same screen. I don't think I quite can get it all on the same screen. So we're going to have to, you're going to have to just remember that or write it down or pause or take a look at the notes. But we're going to substitute in these results that we just got into this expression. And when you do that, what you find is you get minus L plus 1 over IKA times minus 1 over IKA times 1 over 2L plus 1. That we're getting from the fact that JL eta L is equal to this product minus 1 over IKA, 1 over 2L plus 1. And this first term is a JL eta L prime, so we have this extra factor of minus L plus 1 over IKA. And then we're subtracting, we get the same factor of the product of JL with eta L, but now we're looking at the JL prime, so we'll get an L over IKA. And then that equals L over K I times the product of the JL with the JL plus I eta L. The JL squared term is really small because it's a very high power of KA. So it's really just the JL eta L times an I that comes in. So we'll get lambda over K times an I times that same factor minus 1 over IKA times 1 over 2L plus 1. So you actually see that factor of minus I over IKA 1 over 2L plus 1. That appears in every term, so we can just cross that out. We can then multiply both sides by that IKA, and we're actually going to multiply by a minus IKA. And what we find on the left-hand side, what we're left with is L plus 1 plus L, which is 2L plus 1. And on the right-hand side, we're left with lambda over K times Ka, which is just lambda times A. So you see what we get is 2L plus 1 is equal to lambda A. What that tells us is when lambda A is equal to 2L plus 1, a bound state is going to appear at E equals 0 because we're looking at the limit as K goes to 0. So that energy, which is minus h bar squared K squared over 2M, will be approaching 0. So indeed, this is showing us from solving that bound state equation and taking the limit as Ka goes to 0, that indeed that condition for the resonance, the Feshbach resonance, is exactly the condition that a bound state is appearing at E equals 0. This tells us that there is this connection between the appearance of a bound state and a divergence of a scatter amplitude as K goes to 0. In fact, it turns out this connection is true for all K, not just for K going to 0. If we think of the scattering amplitudes as functions of complex K, then bound states appear at the poles of the scattering amplitudes, which is actually an alternative way in which you can solve bound state problems, but it really is a very complicated way of trying to solve a bound state problem. All right, so let's unpack this a little bit more. Let's go back to our delta shell potential where we found the partial wave amplitude. FL of K was 1 over K, Ka lambda A, JL squared of Ka over 1 minus I, Ka lambda A, JL of Ka times JL of Ka plus I eta L of Ka. Note that this is the partial wave scattering amplitude. It is not the wave function that we were talking about before, which is, of course, a function of R, not a function of K. This scattering amplitude has poles when 1 is equal to IKA lambda A, JL of Ka times JL of Ka plus I eta L of Ka. We need to substitute in K equals I kappa and then solve for the poles, and that will give the formula for the bound state energies as being 1 is equal to minus Ka lambda A, JL of IKA times JL of IKA plus I eta L of IKA. Okay, the general rule is that this when we have a positive scattering length, we're going to have weakly bound states and a strong scattering near k equals 0. If we have a negative scattering length, that means we have a pre-bound state and a strong scattering near k equals 0. And in atomic physics experiments, they sweep a magnetic field across this resonance, which is very sharp in the magnetic field, and they can form bound state molecules that are weakly bound, and then they can either study those weakly bound molecules or they can make them into more deeply bound objects. And indeed, there's been a revolution in ultra-cold chemistry that was started about maybe 6-7 years ago when these experiments were done on alkali molecules, and they could form these alkali molecules that have a heat of formation in the electron volts at temperatures that were in the micro to nano Kelvin without heating up the system at all. All of the energy of the formation was taken away by light at the time of the formation. So it's really a quite remarkable experiment that was done there. So if we look at this result for the poles, that does not look like the condition that we had for the k to satisfy, because we had it was equal to I times JL A to L prime minus I A to L JL prime was equal to the right-hand side. We have the right-hand side here, but we have something that looks like the right-hand side times some constants, and we have that it's equal to 1. So we're going to figure out exactly what that connection is in the limit where the Ka is very small as the last topic that we're going to go over in the lecture. Okay, so that's what we're going to do now. And we first want to look at the fact that JL A to L prime minus A to L JL prime is actually something called a Wronskian. And the Wronskian of these spherical Bessel functions turns out to equal 1 over z squared. So I want to verify that for you. So first I'm going to write out what the Bessel equation is in a form that's a little bit different from the form that we were using for solving the wave functions. It takes the form z squared d squared a to l dz squared plus 2z dA to l dz plus z squared minus l times l plus 1 a to l equals 0. And a similar equation for the JL. I'm going to multiply that top equation by JL and the bottom equation by A to L, and I'm going to subtract them. And when we do that, we see we're going to get a z squared JL A to L double prime minus A to L JL double prime plus 2z JL A to L prime minus A to L JL prime equals 0, because the terms that just will have the A to L JL term, they're going to cancel because their coefficients are the same. And now what we do is we notice that first term can be written as d by dz of JL A to L prime minus A to L JL prime. You can see that because if you take the derivative of that term, you're going to get one term that's going to be a JL prime A to L prime, but that will have a term that is subtracted of an A to L prime JL prime, so that will give me 0, and then I'll only be left with the JL A to L double prime minus A to L JL double prime term. So now what we can do is we can rewrite this equation as minus 2 over z dz equals d logarithm of JL A to L prime minus A to L JL prime, because when I take a derivative of something and divide it by the something, that's the logarithmic derivative of the something. So we then can integrate both sides. I'm going to get the logarithm on the right-hand side. I just get minus 2 log z plus a constant on the left-hand side. We then exponentiate, and we get c over z squared equals JL A to L prime minus A to L JL prime. We then are going to take a look at this in the limit where z goes to 0, and that's going to tell us that the constant is equal to 1 just by matching the dominant terms in the limit where Ka is small. And so we have shown that JL A to L prime minus A to L JL prime is equal to 1 over z squared. So we can go back now into this formula that we had here for the bound state here, and we can substitute in for that JL A to L prime minus A to L JL prime with a 1 over z squared, and then plug in, and when we do that, what we find is that we get 1 is equal to minus lambda a Ka, JL of IKA, times JL of IKA plus IA to L of IKA. Now notice, that is the condition when we let Ka goes to IKA. That is the condition for the scattering amplitude for this Feshbach resonance in the scattering amplitude, but it's also the condition that we had for the bound state. So this verifies explicitly for this problem that we were looking at that when we have a divergence in the scattering amplitude, when we've let Ka go to Ika, that is the same equation as we use to find the bound states when we look at the wave functions and when we satisfy the condition that the wave functions decay as r goes to infinity. Okay, that brings us to the end of lecture 24, and this also is the end of our unit on scattering. The Feshbach resonances themselves are really very important in modern experiments that are doing essentially quantum control and quantum simulations of strongly correlated materials, in experiments using individual atoms and manipulating individual atoms and letting the individual atoms move through a lattice, just like quantum particles move through a lattice in solid state physics, except the size of the lattice is about 1,000 times larger. The lattice spacings tend to be microns rather than nanometers, and the time scales are like 6 to 10 orders of magnitude slower. So we can actually study things on microsecond to millisecond time scales, which are occurring in solids on femtosecond time scales. So this is actually a very interesting and active area of research now, and it's one that I have worked in a little bit myself in my career, but I'm not actively working in it right now. Okay, with that, we're going to end lecture 24.